let's talk about zeros first. So, given holomorphic f and z belonging to omega, such that f of z0 is equal to 0. This is called a zero. We've seen these before. Is called a zero of f. Okay, and we've learned some things about zeros, right? We've learned that if we have a collection of zeros inside our domain, then any cluster point can't be inside it. Yeah, yeah. Unless the function is identically equal 0 on that set omega. We're assuming omega is connected. Yeah. Cool. So we know some things about this guy. So that means that zeros are isolated, right? So if we have a 0 inside our set omega, then there isn't another sequence of zeros. There is some ball where there's no other 0 around it. Yeah. Since otherwise it has a sequence of zeros converging to it, and the whole thing is equal to 0. Yeah. So zeros are isolated. So we've learned that zeros are isolated. If f is non-trivial, zeros are isolated. Now let's describe what singularities are. So we say f has a singularity at some point, let's say z1, if and only if f is holomorphic on the punctured ball around z1 for some bigger than 0, but not necessarily defined at z1. This is a star here. I think this is a star on the circle. I think we did define this. This is the set of z such that 0 is bigger than zeta. Set of zeta such that z minus zeta is bigger than 0 but less than r. So it's everything in the ball but not equal to the center point itself. So if f is holomorphic in the punctured ball for some small radius, but not necessarily defined in the punctured ball, defined on the actual value z1. And there's various ways it can be failed to be defined on z1. For example, if we have f of z equals, say, z squared minus 1 over, say, z plus 1, yeah, then what do we know? Then f of 1 is not defined, means nothing. Oops, not f of 1, f of minus 1. F of minus 1 is not defined because at the moment it's just 0 over 0. Yeah? But this is not so much of a problem because you've seen this from calculus lots of times, right? We do this. Right? So if z is not equal to minus 1, yeah, then we can cancel the top and bottom. Then f of z is actually just equal to z minus 1, this nice function. Yeah? Yeah? So we can actually just fill this hole where the function is not defined and create a function that is holomorphic, right? Yeah? So we can define let's call it f tilde of z to be equal to this guy here, z squared minus 1 over z plus 1 if z is not equal to minus 1, and then just equal to minus 2 if z is equal to minus 1. Yeah? Yeah? And that's exactly the same thing as just being z minus 1 for all z. Yeah? So that kind of singularity is pretty harmless, right? Yeah? This is a harmless singularity. And these do occur. This is a very natural expression. This is just a rational function. And sometimes it turns out that the singularities that seem to be there are just not important. We call them removable. It's a removable singularity. You can remove it, and then we have a nice holomorphic function there. Yeah? So it's a removable singularity. Yeah, these are the guys you can basically forget about. Another example. We could have f of z equals 1 over z to some m for m bigger than or equal to 1. Okay? Then f of 0 is not defined as a complex number unless there's a way to actually add infinity to the complex plane where it makes sense, but that's not what we're going to do for the time being. So as a finite complex number, this is not defined. We have a singularity here. Yeah, we have a singularity here. Then f can't be just, you can't make a small change to f and just get rid of the singularity. This is a part of this function. This is real. You know, this guy we can't just ignore. Then if is singular at 0. Yeah, that's a serious thing. However, it's somewhat predictable the way it's singular, because what's happening as we go towards 0, it's going off towards infinity, and it's going off towards infinity in quite a regular way, in quite a standard way. Here's another example. Suppose we have f of z equals e to the 1 over z, like this. Let's think about this guy. Then it's perfectly fine. It's holomorphic everywhere except 0. Yeah. So oops. But at 0, it's got a singularity. It's not defined. And I claim that this guy is very different than this guy. This guy has got a singularity that is much more dramatic than this guy. So I'm going to raise the board. In the meantime, I want you to think about the kind of singularity, what the nature of the singularity is, how this guy behaves as we approach 0, and then tell me about it when the board is erased. Huh? So start by thinking about what does the function e to the z do, yeah? and then put that together with what you know 1 over z does. Yeah? All right. This is our function. F of z equals e to the 1 over z. Tell me about the kind of stuff it does as we approach 0. What does it do? Let's think about what e does. Right? So what is e? So if we have this strip from pi to minus pi, then z goes to e to the z. What does it do? That's the same as x plus iy goes to e to the x plus iy, which is e to the x, e to the iy. Yeah? So what does the exponential function do to this strip? What does it do to the strip? We talked about this. What does the exponential function do to this horizontal line like this? So if you have a horizontal line like this, and the y is fixed, right, and the x varies, what's happening if we plug that into this? You just get a ray, yeah? It'll just give us a ray coming out with this angle like this, yeah? Where this angle is y. What about if we do something like this? So now the x is fixed and the y is changing. It's going to give us a circle, yeah? Yeah? And what will the radius of the circle be? If this thing is x like this, then the radius of the circle will be e to the x, yeah? Yeah? Well, this thing is e to the x. Okay, so what does it do to the strip? What does the e to the x do to the strip? Yeah, it wraps around the entire complex plane. Does it hit everything in the complex plane? It doesn't hit 0, right? So it wraps its entire strip around the entire complex plane except 0. Yeah? And what does it do to the strip above it? The strip from pi to 3 pi. What happens with that? Same thing, right? Same thing. So all of these, we can cut the complex plane into all of these disjoint strips, and each one of them is going to get wrapped around the complex plane. Yeah? Yeah? Pretty wild function. Yeah? Even though it's easy to define, it's holomorphic. Somehow it's able to do that. Yeah? Cool. All right. So that's a little recap of e to the z. Now tell me about this guy. What is the nature of the singularity at 0? Is it the case that we have to approach infinity as z goes to 0? Is it the case that we have to go to infinity as z goes to 0? Is it the case that we can go to infinity as z goes to 0? That's a simpler question. Can we go to infinity as z goes to 0? Here is 0. Let's approach 0. What kind of stuff can happen? What if we approach 0 like this, going like this? We're going along the positive real numbers towards 0. What happens then? Come on. Just goes to positive infinity, right? Because if it's a positive real numbers, right, then this thing just becomes e to some incredibly big positive real number, yeah? So it just blows up to infinity. What about if we go like this? So if we have a very small negative number, yeah, and we put it into this, yeah, we'll have e to a very negative number, right? So the approach is 0. Yeah? Cool. All right, tell me other stuff. What happens as we go down like this towards 0? How many times do we circle? What radius is the circle, for one thing? The radius is 1. How many times do we circle as we go down towards here? Infinitely many times, right? So if we have f of alpha times I, then that is e to the 1 over alpha I, like this. Yeah? And what is this? That is just something of radius 1, so that's the same as e to the minus I over alpha, like this. Yeah? And that is the same as cosine of minus 1 over alpha plus I sine of minus 1 over alpha, like this. Yeah? So as we go down towards 0 with alpha, this thing is rotating round and round. Yeah? And it actually rotates round faster and faster and faster. Yeah? We're going to do infinitely many times rotating around as alpha goes to 0. Do you see what I mean? Yeah, because alpha goes to 0, then 1 over alpha is going to infinity, so we're going along We're going along all these oscillations of the sine and cosine. Yeah, we're going round and round and round and round the circle infinitely many times. You see what I mean, people? Give me a thumbs up if that makes sense. Yeah, cool. Yeah, and the same if we approach from this direction like this. It's going to go round and round. Yeah, which is really, really crazy behavior, right? So it's analytic. It's got a Taylor expansion everywhere except at 0. Yeah. So you might think it's so nice outside of 0, it can't do anything too badly at 0. Yeah? But you're wrong. It does absolutely insane things at 0. As we approach 0 from this side, the function is wrapping around and around and around and around the circle more and more times, infinitely many times, faster and faster. Yeah? As we go on this direction, it blows up to infinity. As we go in this direction, it's going down towards 0. Yeah? So there's a whole variety of different things this thing will do as we approach 0 from different directions. Yeah? So it's a dramatically strange and weird behavior here. Yeah? And as we do some kind of line going in some direction, we get some combination of these behaviors. Yeah? So you can spend a long time figuring out all the possible weird behaviors that you can get out as you approach 0 from these different directions. There's a whole zoo of different behaviors at this particular singularity. Yeah? It's just really sort of weird because it's so easy to describe, to write down, but it contains a whole massive amount of different information about how it's behaving as we approach 0. So this is a very different kind of singularity than the previous singularity of 1 over z to the m. Yeah? And certainly very different than the removal singularity. Yeah? This is dramatically harder to understand behavior. Yeah? And this is what we're going to call, well, this is an example of something called an essential singularity. So this is an essential singularity, which we'll define later. This is a kind of warm-up of the kind of things you're going to see. So when we talk about singularity, we're going to have 3 types. We're going to have removable singularities, which are basically like things we don't have to care about. We're going to have poles, which are singularities that definitely exist, and there's no getting around that. But they behave in a very predictable way, in a way we can manage. And then there's these guys that behave in an insane way, completely insane way. And these guys, we can't manage, we can't do anything with them. We can't control the function, we can't understand the function around these guys. We can prove some theorems about how wild they are, but when we have a function with essential singularities, many of the things we'd like to do are much harder. This is singular. Cool. All right. So that's what we're going to learn about in this section.